Welcome all. So, today we will continue from the last time where we are seeing the effect of the blast loading on the structures. We learned how to calculate the effect of the blast loading at a given point. Then we learned how to apply the blast loading on the structures, calculate the equivalent pressure time curve, so that the equivalent pressure time curve can be applied to the structures. We saw what are the approximations that we need to apply. Okay. So, we will continue from the same trend. Okay. So, last time we have looked into the walls, the front walls. The structure was above ground, it has a rectangular configuration and the shock front was acting parallel to it. Okay. Now, we are moving and we are looking into a case where the shock front is oblique. Okay. It means that it is acting at an angle. Okay. So, we see this is in plan and this is in elevation. So, we see that the shock front is acting at an angle to the blast loading. Okay. So, in our last treatment we saw that the shock front is acting directly to the structure. Okay. And this was the constructed equivalent pressure time curve. Okay. Now, the pressure front is moving at an given angle. Okay. So, again we have the similar type of treatment. So, instead of the direct reflected pressure, it will see a component of that. Okay. So, when the shock front approaches at an oblique angle alpha, the peak reflected pressure depends upon the incident pressure. Okay. It will depend upon the incident pressure, the interaction between the incident pressure and the structure, and the angle at which it is attacking the structure. So, in order to calculate the fictitious duration, okay, we will take the angular component, okay, where R alpha and PR alpha are discussed ahead. Okay. So, this is nothing but the angular component of the pressure that is hitting the structure. Okay. Rest of the treatments remains the same. Okay. After time Tc, incident pressure and the drag pressure acts on the structure. Okay. And similarly, the negative phase is being constructed. Okay. And there is a gap between the positive phase and the negative phase. Okay. So, negative pressure phase is included when we are calculating the overall structural motion. Okay. Okay. So, this is a simplistic curve, okay, in which the angle of incidence is used, okay, to calculate the reflected pressure coefficients versus angle of incidence. Okay. So, using this curve we can directly calculate the reflected pressure coefficients, and these curves are given as a function of peak incident over pressures. Okay. So, these curves are as a function of incident pressures, and using these curves we can calculate, okay, for any given angle depending upon the peak incident angle, we can calculate the reflected pressures. Okay. So, all these curves are given in UFC 340. Okay. And similarly, they are also present in TM5 1300. Okay. So, which is nothing but everything has now been ascribed into UFC 340. Okay. So, these curves can be generally used for the design purposes. Okay. The good thing about this manual is that there are a lot of curves, and each and every type of blast loading, okay, free air blast, air blast, surface blast, confined blast, everything has been categorized and neatly the curves have been presented. Okay. So, these curves are a result of different experiments. Okay. So, maxima of these experiments have been taken. Okay. So, basically an envelope has been created, and using this envelopes anything can be, like the normal quantity that is put in the x axis is the quantity z. Okay. And using that quantity we can calculate any blast parameters, and here also using the incident angle we can calculate the reflected pressures depending upon the magnitude of the incident pressures. Okay. So, this is for a specific case, this is for the front wall loading case. Continuing ahead. So, now we looked how to construct for the front wall. Okay. Now, we are looking for the construction of the roof and side walls. Okay. So, the shock front is transverse, okay, and its effects on the roof and the side walls. Okay. So, as the shock front passes over a structure, roof slab and the side wall experiences incident pressure at a given time and point, okay, and they are reduced by negative drag pressure. Okay. The portion of the surface loaded depends upon magnitude of the incident pressure, location of the shock front and wavelength of the blast loading, okay, the negative wavelength and the positive wavelength. Okay. So, accurate loading determination requires step by step wave propagation analysis. Okay. We need to integrate pressure at various points. Okay. So, integration in time as well as in space, okay. And then we have to derive equivalent uniform incident pressure versus time for a given span length L. Okay. So, this treatment is for the side walls and the roof walls. Okay. And here we have taken a section through the structure. Okay. So, continuing ahead, we have a uniform pressure assumptions. Okay. So, during the shock front travel, there is a point of inflection across the element changes. Okay. So, we assume a uniform pressure distribution, okay, and it is valid only if reinforcement is continuous on both faces across the span. Okay. So, normally in blast loading we reinforce it uniformly, okay, so that our uniform pressure variation is justified. Okay. So, during the transverse, okay, during the traverse of the waves, okay, the wave characteristic includes an incident peak pressure decay and the wavelength increases. Okay. So, pressure time profile, so it increases linearly from Tx to T. Okay. So, a wave hitting start point to Td, shock front reaching point T, and there is a peak uniform pressure. Okay. Then it decreases to 0 at the load point B drops to 0. Okay. So, this is how the behavior of the blast load, okay, occurs on the roof and side walls. Okay. So, this is the signature of the blast pressure, okay, and this signature will be used to calculate the forces on the roof and the side walls. Okay. So, we use a simplified calculation approach. We assume a equivalent uniform pressure, and this is expressed using the blast wave parameters. Okay. So, the key parameters are equivalent load factor that we can get from the figure 7, rise time again from the figure 7, duration. Okay. So, using all these parameters, okay, we can calculate the equivalent forces, okay, and all these things are given as a function of wavelength to span ratio, okay, and the peak roof pressure can be calculated using this equation. Okay. So, PSOF, okay, this guy is the incident pressure at a point, okay, this is the dynamic pressure continuing to the drag coefficients, okay, and CD is the drag coefficient. Okay. So, using these equations we can calculate the signature of the pressure on the side walls as well as on the roof. Okay. Our assumption remains the same, there is a uniform pressure acting on the structure is located above ground, it is rectangular in nature and it has no openings. Okay. So, what we are trying to do is that we are trying to calculate the signature of the blast loading at a point, and from there we are transmitting it to the design curves, okay, the equivalent design curves for the design of the different elements, front wall, side walls, roofs. Okay. Okay. So, we can use this curve also. Okay. This curve also follows the same parameter here. Okay. So, this is the figures 7, 8 and 9. Okay. So, this is figure 7. So, using figure 7 we can calculate the equivalent positive pressure coefficients and the negative pressure coefficients, okay, and that are given in terms of the incident pressures. Okay. So, equivalent load factor we can calculate, okay, using figure 7. Okay. Same thing we can calculate the rise time of the equivalent positive roof pressure. So, here scaled rise time is there, okay, and that also is given as a function of the wavelength. Okay. So, blast wave parameter at a point. So, we can calculate the rise time using figure 8, okay, and after doing all those things we can calculate the reflected pressure. Okay. Figure 9. So, using the same wavelength parameter we can calculate the scale duration also, okay, and they are all scaled quantities, and when multiplied by cubic root of W, that they will give the equivalent quantities in the respective units. Okay. So, figure 7, 8, 9, okay. Subsequently, if we use, we can calculate the all the functions, okay, and this all are as a function of the wavelength to span ratio. Okay. This is the wavelength to the span ratio. Okay. So, all the functions can be calculated easily from using the curves, okay, figure 7, figure 8 and figure 9. Okay. Okay. Again continuing the treatment. Okay. So, the drag coefficient for roof and side wall, they are calculated as a function of the peak dynamic pressure. Okay. So, we have some recommendation depending upon the blast design manual. So, the pressure range from 0 to 25, minus 0.4, 25 to 50, minus 0.3 and 50 to 130 is minus 0.2. Okay. So, these values we can use to calculate the drag coefficients. Okay. So, the drag effect acts opposite to the incident pressure direction. So, this is important to the side wall where flow separation and suction significantly alter net pressure. Okay. So, this comes into picture in the roofs and the side wall where there is a suction component also occurring. Okay. So, using all these quantities, okay, we can calculate the effect of the reflected pressure on the side walls and the roof. Okay. Okay. Now comes the rear wall. Okay. We have looked into front wall, we have looked into, so if this is my structure, okay. So, we have looked into the front wall, we have looked into the side walls, okay, and we have looked into the roof. Okay. Now, we are looking into the rear wall, okay, and all these assumptions are being considered, treating that there is no opening in the structure. Okay. So, what happens in the rear wall? Okay. As the shock front passes over the rear edges of the roof and side walls, the pressure front expands, forming a secondary waves. Okay. So, till it reaches the rear wall, there is the formation of the secondary waves. Okay. So, the secondary waves propagate onto the rear wall of the structure. So, the second waves are hitting the structure. Okay. So, there is a formation of the secondary waves by the time it reaches the rear wall, and the secondary waves interact with the rear wall. Okay. So, for long buildings, okay, if the building is very long, okay, so by the time it has hit the front wall and it has gone over and it has reached the rear wall, okay, there will be a significant formation of the secondary waves. Okay. So, the secondary waves on the rear wall, they are a result from the spillover of the waves from roof and the side walls. Okay. Whatever is remaining from the side walls and the roofs, the secondary waves then will hit the rear wall. Okay. So, as a principle, secondary waves, the reinforcements in the rear wall, okay, reinforcement of roof spillover waves comes from the reflection of the ground at the rear wall base. Okay. The accumulation of the magnitude in the pressure. Okay. So, the accumulation of this waves comes from the reflection of the ground at the rear wall base. Okay. At the base of the rear wall, okay, if this is the rear wall, due to the reflection from the ground, there the secondary waves are strengthened. Okay. Okay. So, the secondary waves are reinforced by reflections from the ground, okay, at the rear wall base. Okay. So, if secondary wave is coming at the rear wall, okay, due to the reflections of the ground, okay, there will be an increase in the magnitude of the secondary waves. Okay. Plus, it is also augmented by the secondary waves, okay, which are occurring in the side wall. Okay. So, there is a collision between those waves near the center of the rear wall and or interaction with the roof waves. Okay. Basically, what it is saying is that one interaction comes from the ground of the rear wall, one interaction comes from the side walls and the roof. Okay. So, all these things adds up and reinforces the secondary wall. Okay. Reinforces the secondary waves which is hitting my rear wall. Okay. So, due to the interaction of the secondary waves, okay, with the ground, okay, it is being reinforced, and it is also being reinforced due to the waves that is interacting from the side walls and the roofs. Okay. So, overall effect of this reflection on rear wall loading is not fully quantified. It is not exactly accurately defined, but we will take some approximations. Okay. So, this augmentation of the secondary waves, okay, due to the ground and due to the side walls and the roof is not fully understood, but we will take some approximations so that the design of the rear wall can be done. Okay. So, rear wall load calculation methods, it follows the same principle as the side wall and the roof wall. Okay. So, blast load on the rear wall can be estimated by the equivalent uniform pressure method used for the roofs and the side walls. Okay. So, the same assumptions for the roofs and the side wall is applied, and the pressure is assumed as an equivalent uniform pressure. Okay. The peak pressure of the equivalent uniform pressure time curve is based on the peak pressure at the back edge of the roof slab. Okay. So, in the roof slab, if this is the roof slab, so at the back edge whatever is the peak pressure, that pressure is being used for the calculation of the pressure at the rear wall. Okay. So, it makes sense, whatever is occurring at the last end of the roof slab, that is applied as the peak pressure of the back slab. Okay. So, equivalent uniform load factors like C and C negative, rise times and duration of the positive and negative phases are obtained as a function of wavelength of the peak pressure and height of the rear wall. Okay. So, depending upon the height of the rear wall and the wavelength of the peak pressure, the uniform load factors are assumed. Okay. So, what this method is doing is that this is integrating the effect of the blast atmosphere around the rear wall for design simplicity. Okay. And this is the equivalent curve which is being used for the design of the rear wall. Okay. And it has the same treatment as the roof and the side walls. Okay. So, incident pressure is there. Okay. So, this peak pressure is the pressure that is occurring at the back end of the roof wall, and these are the pressures due to the drag. And this treatment is given in UFC 330. So, rear wall drag and oblique angles. So, to calculate the drag coefficients and the oblique angles. So, what blast load is doing is that it includes the drag pressure in addition to the incident pressure on the rear wall. So, here we see the total component comprises of incident pressure and the drag coefficient. So, it has two components, one due to the incident pressure, one due to the drag component. Draining pressure of the drag corresponds to the equivalent pressure. Recommended drag coefficients CD are the same as those used for side and rear walls. So, whatever the treatment we saw for the rear wall, the values of CD for roof and the side walls, the same factors, the same table can be used for the calculation of the pressure on the rear wall also. The same as used for the roof and the slide wall. If rear wall is at an oblique angle to the shock front, if the shock front, if this is my rear wall and the shock front is at an angle, then the peak incident pressure should be calculated at the mid width of the rear wall. So, the peak pressure is calculated at the mid width. If this is the width W, then it is calculated at the mid width. What this approach is doing is that this approach is helping capturing combined pressure and the aerodynamic effect on the rear wall accurately. If we move at any edges, then what might happen is that any of the component can be underestimated. So, to estimate those two quantities accurately, we calculate all these quantities at the mid width. So, both the components using the incident and the drag components are calculated at the mid width. And here you can see again there is a gap between the positive and the negative phase. So, this is the equivalent design pressure curve that is used for the design of the rear wall. Similarly, this curve was used for the design of the roof and side wall, and this curve was used for the design of the front wall. So, we have covered the equivalent pressure loading that has to be implemented for the front wall. We have seen the similar equivalent loading for the roof and side walls, and similarly the equivalent pressure loading for the rear wall. Okay. So, all the faces of the wall has been covered out here. Okay. Okay. Now, we have looked into the case of one explosion. Okay. Now, we will try to see what happens during a multiple explosion. Okay. So, we looked into the effect on the blast parameters. Okay. During a multiple explosion, what happens to a blast parameters? Similarly, we are extending the same thought and looking into what happens during a multiple explosions, what is the effect on the structure. Okay. So, in the first phase, we completed the calculation of the blast parameters, then we applied the blast parameters on the structure, and on the different component of the structure, different phases of the structure, we calculated the equivalent design pressure loading, and this pressure loading was due to one explosion, and now we are looking into the multiple explosions. Okay. So, step by step we are building our case, okay, so that we can put the pressure loading and change it to a force and then design the respective structural components. Okay. So, during a multiple explosion, what happens during a multiple explosion? Okay. So, the structure far from multiple explosion may experience a series of separate pulses rather than a single blast pulse. Okay. So, if my structure is located sufficiently away from the multiple explosions, okay, if this distance is significant enough, so what it might see is a series of separate pulses, okay, rather than a single blast pulse. Okay. So, it will see that one has hit, after some time the other one hits, and after some time the third one hits. Okay. Instead of a combined blast pulse, okay, it will see a series of separate blast pulses if the structure is far away from the multiple explosion site. Okay. So, multiple pressure pulse loading typically occurs with small explosive weights. Okay. So, if the explosives are small, okay, if the charge is very small, or if it is located significantly far away from the structure, then the structure will see separate pulses, okay, instead of a combined blast pulse. Okay. So, this type of loading is uncommon for usual design cases involving large explosions. Okay. So, this type of loading, okay, is not conventionally used. Okay. Conventionally, what we design is that we design for a large explosion. Okay. We will take the worst case scenario of the weight and we will take the distance as close as possible depending upon the occupancy of the structure and the accurate placement of this loading, okay, the worst placement of this loading, and we will design the structure for this case. Okay. Normally, the design for multiple small blast event is not done. Okay. So, for large combined explosive weights, blast load may exhibit single pressure pulse with multiple peak pressure. Okay. So, for the combined explosive weights, blast loading may exhibit single pressure pulse with multiple peak pressure. Okay. It means that the loading is combined, but it is peaking at different instances. Okay. So, there is no specific method currently available to precisely evaluate such complex blast loading. Okay. Blast loading in itself is very complex. Okay. A single blast loading, as we have seen, okay, there are many assumptions. Okay. We are assuming uniform blast loading, we are assuming above ground structure, rectangular structures, okay, and this when combines with the multiple explosion case, the analysis becomes much more complex. Okay. So, right now we do not have a precise methodology, okay, we do not have a cookbook to evaluate this thing. Okay. Either we can do a finite element simulation, or what we can do is that we can evaluate the state of stresses, okay, during one explosion, keep that state of stress, okay, as a end condition or as a starting condition. So, the end condition of the first one will be the starting condition for the next evaluation, and we can progress like this, okay, in a chain manner. Okay. But that itself is also very tedious task. Okay. So, designing directly from multiple peak pressures is challenging due to the complexity of the blast wave interaction. So, as we were saying, even during a single blast load, it is very tedious to design. Okay. And this when combined with the multiple blast explosions, it augments the total blast analysis. Okay. So, this is a tedious process and it has to be taken into account, okay, either by the finite element analysis or using this end condition, initial condition, end condition, initial condition rule. Okay. So, we will try to do one example. So, we are trying to find a blast wave parameter for a surface burst. Okay. So, charge is given as 20,800 pounds, okay. Ground range is 530 feet, and we are asked to calculate the blast wave parameters. Okay. So, first thing we will take the weight of the charge, okay, and we will convert into the equivalent charge. Okay. So, if it is other than TNT or something, to account for the 20% uncertainty, we multiply it by 1.2. Okay. So, we get the blast wave parameter. Okay. After that, we need to see, depending upon the location of the charge with respect to the ground, we need to categorize this thing as a free air blast, okay, surface blast, okay, or air blast. Okay. After that, we need to calculate the distance between the blast and the point in question. Okay. So, we need to calculate the standoff distance r, and from the standoff distance r, we need to calculate the quantity z. Okay. Okay. And then we will put this thing into the equivalent charts, and we can calculate the all the required quantities. Okay. So, first of all, we calculated the equivalent weight. After that, depending upon the conditions, okay, we categorize into the type of blast. Okay. Then we calculate the R factor, and then we calculate the Z factor, and after that, using the appropriate chart, okay, depend upon the type of blast loading, we calculate the different parameters. Okay. And normally these parameters are given scaled in terms of Z. Okay. So, let us say if you are reading from the chart, it will be given as a scaled quantity. Okay. Then we need to multiply with the equivalent weight, and then we can get the actual quantities in the range. Okay. And once we have these quantities, okay, once we have these quantities, then if this thing is occurring, if a structure is given, okay, if the structure is given, okay, and this blast parameters are calculated. So, after these things, using the equivalent graphs, okay, using the equivalent curves, okay, we can calculate the pressure profile that is acting on the front load, front wall. We can calculate the pressure profile, okay, the equivalent design pressure profile that is occurring on the side walls, that is occurring on the roof, and that is occurring on the rear wall. Okay. So, till this point, what we have learnt is, we have learnt to categorize the blast loading, we have learned to calculate the parameters of the blast loading, we have learned to calculate the equivalent design pressure curves, okay, design pressure curves for a blast event, okay, in which a structure is located. Okay. The assumption of the structure is that it should be a rectangular structure and it should be overground, and if those cases are met, we are able to calculate the equivalent pressure curves, okay, equivalent design pressure curves on all the 5 surfaces of the structure. Okay. So, I will ask to practice these things, okay, be familiarized with the UFC 3340 manuals, take out the graphs, okay, try to go through the things. We have tried to give some examples and try to recalculate those examples and see if these are done. Okay. I wish you good luck. Thank you.